So yeah, so the question is, was there a reason for choosing the beta distribution as a prior? Yeah. So the reason for choosing the beta distribution is um, two things, right? One is that with the beta distribution, it turns out that you can compute the posterior distribution easily compared to others, right? Because the prior distribution is yeah. So if you see over here, right? So yeah, so we have a so first of all, we want two things. We want the beta distribution to encode some kind of a prior knowledge, right? And I think the beta distribution kind of has this nice uh, distribution around the kind of mean parameter, right? So the parameter here is the probability of my kind of prior probability of my coin flip, right? So actually, sorry, I'm using a different app today, so there's going to be a little bit of a delay, unfortunately, because I had to connect through Blackboard Collaborate. I'm using my Windows machine. So because of this, I'm having to mirror my screen, unfortunately. So it's going to be a little bit of a lag, but let's hope it's not too much. So the first reason is that with the beta distribution, you can model based on this beta h comma beta t parameter, right? You can model how much you want the distribution to be peaked, right? So for example, if beta h and beta t are very large, the more the peaked will be the prior distribution, right? And if beta h and beta t are small, so for example 2 comma 2, then we have this to be kind of fairly more uniform, right? 1 comma 1 is the most uniform because 1 comma 1 is just flat, right, between 0 to 1. Again, because theta here is a probability, so theta is a probability that a single coin toss will be heads, right? So theta will always lie between 0 to 1. So my probability distribution will only have mass between 0 to 1. And in some sense, beta kind of, you can both model the width based on the beta parameter, and you can also model if you want it to be more towards, you know, the right hand side or more towards the left hand side, right? Depending on if we assume if we have our prior belief theta to be less than 0.5 or more than 0.5, right? Depending on that, the beta will either be tilted to the left hand side or it will be tilted to the right hand side. But the second and more important reason why you have the beta is because with the beta distribution, right, you can actually compute the MAP actually efficiently, right? So yeah, so essentially, if you yeah, so if you come to this, if you come to this slide, so we have the probability. Yeah, so this is the probability. So we want the probability of theta given d, right? So this probability is proportional to p of d given theta multiplied by p of theta, right? So now p of theta is actually beta distribution of beta h comma alpha h, right? And we have our normal likelihood function, right? This likelihood function was our standard kind of Bernoulli distribution, right? So this was basically Bernoulli distribution of alpha h comma alpha t. And actually, sorry, this is beta h comma beta t, right? So when you multiply these two, when you multiply the Bernoulli distribution, it turns out that maybe I'll just add a slide here afterwards. Okay. So just a little bit more about the MAP, right? For coin flipping. Okay. So we saw that if I'm given my data set comprises of alpha h number of heads, right, and alpha t number of tails, right? Then the likelihood probability, right? So the probability of given a theta, right? Given a theta, the probability that I will witness alpha h. So this is my data set D, right? So the probability that I will witness this is nothing but basically theta raised to alpha h multiplied by 1 minus theta raised to alpha t, right? And this is, recall that you have, so the data set D comprises of one specific sequence, right? So it comprises of one specific sequence x1, x2 up to xn, right? And xi is either 0 or 1, depending on whether it's a heads or a tails, right? So basically alpha h plus alpha t is equal to n, right? So in my sequence over here, I have that, I have alpha h number of heads and alpha t number of tails, right? And then we saw that if we just look at likelihood, if we just look at MLE, right? So then what we will do is we will maximize theta, sorry, we'll maximize theta of P of D given theta, right? And this is nothing but maximizing theta over theta raised to alpha h 1 minus theta raised to alpha t, right? We did the math over here, right? So we did the math, and then you can basically do a couple of things. You can first of all take the derivative with respect to theta, right? On both sides. So actually, okay, so one thing, sorry. So what you oftentimes will do is that you will actually maximize log of P of D given theta, right? So essentially it is log of this quantity. It's the same actually if you take the log or if you don't take the log, right? But just that the log makes it slightly easier. So maybe I'll just write one more step over here. So this will turn out to be nothing but alpha h log theta plus alpha t log 1 minus theta, right? And then we take the derivative with respect to theta. So then taking the derivative with respect to theta, right, is nothing but alpha h over theta plus, uh, actually it's minus alpha t over 1 minus theta, right? And this should be 0. So this actually gave us that theta is nothing but alpha h over alpha h plus alpha t. So I'm just kind of going over this again so that everyone is clear. And then we saw with the MAP, right? The MAP, the maximum a posteriori estimate, we care about maximizing theta of log of P d given theta multiplied by P theta, right? There is also divided by P of D. Okay, so you also divide by P of D, but in terms of theta, P of D is a constant, so it doesn't matter. Okay, so now in the case of the MAP, right, we will basically get again this term, right? So we will get log of P of D given theta, right, plus log of P theta, right? And then you maximize theta over this expression. So now the reason why you choose the beta distribution, one of the reasons is because the beta distribution exactly satisfies this, that P of theta actually is proportional to theta raised to beta h minus 1 multiplied by 1 minus theta raised to beta t minus 1. Okay, so if you multiply if you multiply this term with this term, right, what you will get is you will get, so maybe I'll just erase this actually, because if you directly look at this, this becomes a little easier, right? So P of um, P of theta is this. So that means that P of D given theta multiplied by P of theta will be nothing but theta raised to alpha h plus beta h minus 1, right? Multiplied by 1 minus theta raised to alpha t plus beta t minus 1, right? So that's how we actually get with the theta MAP, if you remember, right? You get that theta MAP is actually equal to alpha h plus beta h minus 1 divided by alpha h plus beta h, right, plus alpha t plus beta t minus 2. Okay, so in some sense, the MAP essentially takes this beta parameter, so it does this kind of smoothing. Sorry, as I said, there is a little bit of a delay, but yeah. Does it answer your question actually?
I think it does. Yeah. So using the beta distribution, not only does it make it easy to calculate the max the posterior thing, but it also makes it also is a good choice because it allows you to control where the peaks are.
Yeah, exactly. So it allows, depending on what, so the prior distribution, right? So in some sense, this is a very intuitive expression, right? It has both the alpha h and alpha t, right? And it also has the beta h and beta t. So typically one thing we want to do is we don't want to be too sure of our prior, right? So we want our prior to be small. So for example, you will pick you will pick the prior such that beta h is say equal to 2 and say beta t is equal to 2, right? Suppose our prior is basically that it should be basically the coin should be a fair coin, right? It may be possible that we believe that the coin may not be a fair coin, right? In which case we could maybe tilt it one way or the other. So we could say, for example, beta h is equal to 2 and alpha beta t is equal to 3, in which case we are reducing the probability of heads a little bit, right? Or vice versa. But either way, right, this number would hopefully be small. Sorry, what am I doing? So hopefully this number would be small, right? So in comparison to alpha h, so as my alpha h increases, so imagine we see like 1,000 heads, right? And we see like say 3,000 tails. Compared to 1,000 heads and 3,000, so in that case n is 4,000, right? So compared to 4,000, 2 is a very small number. So beta h and beta t would hardly change the distribution, which actually makes sense, right? We don't want our prior distribution to enforce too much if we have a lot of data. But if I have very less amount of data, so if I have only 5 or 10 observations, right? Then we want the prior distribution to give some kind of smoothing, because I don't want to be overconfident with very less amount of data. So that's why my prior, so I think that's the main takeaway of the prior distribution. Okay. So prior distribution really becomes very useful in scenarios where you have very less amount of data. And as n becomes very large, or as alpha h and alpha t become very large, we want that our distribution should become more and more similar to maximum likelihood. Our MAP and maximum likelihood should become the same. Does it make sense? I think this is the main bottom line of probabilistic modeling, right? And that's where maximum a posteriori essentially makes most amount of sense, right? Where I kind of want to enforce a prior distribution in the less data regime. But as I get more and more data, I want my data to be able to make the decisions, not my prior belief, right? Because in the event that I'm getting infinite amount of data, obviously the patterns from the data will become very, very clear. Okay. So were there any other questions? Unfortunately, because of the team's outage, we lost quite a bit of time. But I still think that we should be able to complete the Naïve based section today, right? So this is actually lecture 10, and today we'll try to cover Naïve Bayes, right? So Naïve Bayes is kind of a natural succession from the Bayesian methods lecture from last time, where we studied maximum likelihood and maximum a posteriori estimation, right? And yeah, with respect to the homework, so just a quick announcement that I am working on the homework assignment right now, to basically assignment 2. So I'm hoping that either today night or tomorrow morning, I'll be uploading the assignment 2. Okay, so the assignment 2 will be till basically Naïve Bayes roughly. I mean, I don't think there'll be a question on Naïve Bayes, but there'll be a question on maximum likelihood estimation. Okay, so last time, yeah, so last time we looked at parameter learning, right? And we looked at basically the simple example of a coin flip model, right? And we looked at the idea of prior distributions and posterior distributions. Okay, so today we will actually build upon this and look at more parameter learning, and particularly look at look at the first. Will it be due in 2 weeks? Yeah, so it'll be due in roughly 2 weeks. So I think it'll be due around the week of 10th roughly. I think 10th or 11th, that's a Friday. So that's when this homework will be due. And when will the grades for homework 1 come out? So I think the TA is right now grading the homework. So the grades will most likely come out by the end of this week. Okay. Okay. So maximum likelihood estimation, we have our data comprising of a set of alpha H heads and alpha T tails. Remember that this is a very specific sequence of alpha H heads and alpha T tails, right? And the hypothesis is that the coin flips follow a binomial distribution. So each coin flip follows a binomial distribution, right? So find the best theta, right? So theta here is the parameter of an individual coin flip, right? So an individual coin flip basically is like a beta distribution on theta. Sorry, a binomial distribution on theta. Okay. And the maximum likelihood estimation is to choose the theta which maximizes the likelihood, and it is the probability of d given theta, right? So this is MLE, and we saw how to do this for the coin flip case, right? And then the maximum a posteriori distribution, which is also called the MAP estimation, right? This basically looks at theta map as doing the argmax of p of theta given d, and this is nothing but p of theta multiplied by p of d given theta divided by p of d, right? And this term is independent of theta, sorry, right? So this term is a constant, so I think basically you can just say that this is proportional to just the numerator. Okay. So the difference between theta MLE and theta MAP is that one assumes a uniform prior, right? So it assumes that P of theta here is a uniform distribution, whereas the other allows for arbitrary prior distributions. Okay. Okay, so now we look at one more example, and this will be a kind of more continuous distribution here. So we look at the Gaussian distribution. Okay, so Gaussian distribution is I am given kind of instances of x here, right? So I'm given essentially various values xi, right? And each of the xi's follow this Gaussian distribution with mu and sigma, right? So here there are two parameters. So the coin flipping model, we had just one parameter, right? In the case of the Gaussian distribution, we have two parameters. So this is my theta, and the first parameter my mean, and my second parameter is my variance. Okay. And the Gaussian distribution P of x given mu comma sigma is nothing but this probability distribution, right? So the distribution is the normalization factor, which is 1 over sigma square root 2 pi. Okay, so this is just the normalization factor. The normalization factor just makes sure that the integral of this is 1, right? And it is over e raised to minus x minus mu the whole square divided by 2 sigma square. Okay, so one important thing is that the Gaussian distribution, okay, is centered around the mean mu. Okay, so this blue line is nothing but a Gaussian distribution with a mean equal to 0. So this is, by the way, all one-dimensional Gaussian. Okay, so you can also do multi-dimensional Gaussian, but those are much more complicated. So this is all one-dimensional Gaussian. So this is the mean over here, mu, right? Mu equal to 0. And sigma is the variance, right? So variance is also nothing but the kind of the breadth of this distribution, right? So here the variance sigma square is 0.2. Okay, so smaller the variance, smaller will be the breadth. Okay, so larger the variance, so I think this one has a variance of 5, right, which is the kind of yellow Gaussian distribution. So this is like very flat. It kind of gets more and more like a uniform distribution as my variance increases. Okay, and um, and this is kind of in between, right? So this is for different values of mu and sigma, and this is how this is plotted. Okay, so intuitively, I think one more important thing is that the Gaussian distribution has, so like the coin flip model, theta, the value of x, right? Because x, so in the coin flip case, right, I had my distribution, and my distribution was always between 0 and 1, right? because, sorry, again, there's a lag actually a little bit. So in the coin flip case, right, I had my theta, right, and then I had my probability over here, right, and my probability is nothing but between 0 and 1. Okay, so let's just give a minute for the lag. Yeah, I think I just need to write less actually when I use this app. Sorry about that. Anyways, any questions so far? I didn't realize it was this bad for. So actually, what is collab? Yeah, no, I don't think it's collaborate, which is bad. It's just because I'm using my kind of Windows machine this for setting up collaborate, because somehow I could not log in to collaborate with my Mac. I'm using another app to sync with my iPad, and I think it's just somehow lagging with the uh, with the AirPlay somehow. The issue. But anyways, just for this lecture, just have to bear with me. So anyway, so some properties of Gaussians, right? I think this is pretty clear. So the let's see. Yeah, so the Gaussian distribution, right? X here, X follows a distribution which is normal of mu comma sigma square, right? So mu is the mean and sigma is the variance. And then it also has the following properties. Okay, so if you define y, my variable y, kind of a new variable to be ax plus b, okay, then if x follows a distribution of normal of mu comma sigma square, then y will follow a distribution of the where the mean is a mu plus b, right, and the variance is a square sigma square. So it's actually not very hard to do the math for this to prove this, but I'll probably leave this up to you to do. But it just follows by looking at essentially this distribution, right, and then trying to match back the mean and the variance, right. um, Anyways, so in fact this actually follows from simple rules actually from expectation. So the expectation of y, right, the expectation of y is essentially the expectation of, sorry, so this is the expectation of ax plus b, right, and this is nothing but a multiplied by the expectation of x. Okay, but b is a constant, right? So because b is a constant, the expectation of a constant is just going to be b, right? So this is nothing but a multiplied by the expectation of x plus b, right? And the expectation of x is mu, right? So that's why this is basically a mu plus b. And similarly, you can also get this for the for the variance, right? So this is also a normal distribution, but the mean is a mu plus b and a square sigma square. So the only thing which you need to prove actually is that this itself is a normal, right? So if x is a normal distribution, then y, which is ax plus b, also is a normal distribution, and that can be shown by just expanding out the terms here for mu and sigma square. Okay. It also turns out that the sum of Gaussians is a Gaussian distribution. So if my x is a Gaussian with mu x comma sigma x square, and a y is a Gaussian with mu y comma sigma y square, okay, then z is equal to x plus y, and then z follows a normal distribution with mu x plus mu y and sigma x square plus sigma y square. Okay. Okay, so what is an application of a Gaussian distribution, right? So imagine you have exam scores, right, where each individual has, you have a basically say we have a midterm exam, right, and this is a distribution of exam scores by the different students. So the question is that does this distribution fit a Gaussian? Well, it turns out that a Gaussian is a pretty good estimate as you get more and more amount of data, right? So Gaussian is a pretty good model you can fit for these kind of quantities, right? And if we were to fit a Gaussian distribution, right, then how would we estimate the mean and the variance parameter, right? So the machine learning question over here is that given instances, which is 1, 2 until m, right? So I have capital M number of instances. Then how can I learn my parameters, which is mu and sigma, right? So well, I can do it again similarly using maximum likelihood estimation, right? So I have my D samples, which are x1 to xn. So here I've used capital N, right, as a total number of samples. So I can write down the distribution. So essentially each of my distribution, each of my xi given mu comma sigma, okay, this is nothing but 1 over square root 2 pi sigma square over e raised to minus x. I'll just use x capital I mean x sup instead of sub, x sup I, okay? So this is x sup I minus mu square over 2 sigma square. So this is the probability distribution of one instance. And when I'm computing the distribution over the entire data, it is nothing but the product of all of these guys, right? So this is nothing but the product of I from 1 to capital N P of xi given mu comma sigma, right? So that's how I get this distribution, okay? And then what I can do is that I can define this. Okay, so actually here I can take a log. So typically this is the log likelihood, right? So the mu MLE and sigma MLE is nothing but where I take the log of this quantity, right? So now what this means is that I can compute the log likelihood, log of P of mu, or P of D given mu comma sigma. And this is nothing but this, right? The reason is because when you take a log of the first term, right? The log of the first term is nothing but minus n over log 2 pi sigma square, right? Because of the square root, I get the half over here, okay? Minus, because there is a e raised to minus term, and when I do the log, it is nothing but minus sum of the sum of the quantities from I from 1 to capital N of xi minus mu square divided by 2 sigma square, right? So this also is very intuitive because I am essentially given my Gaussian distribution. I'm just taking the sum of the yeah. So Gaussian distribution. Yeah. So Gaussian is another name for normal distribution. Yes, that's correct. That's correct. Yes. So yeah. So this is basically the expression for the log likelihood, right? So the first term is independent of mu, just depends on sigma square, and the second term depends on both mu and sigma square, right? So now the question is, how do I compute my MLE parameters, right? So the MLE parameters are actually pretty easy. First is I just take the derivative with respect to mu and to 0, right? So it's basically the gradient with respect to mu. But essentially over here, I'm assuming that my xi's are all real numbers, okay? So that means that my mu is also a real number and my sigma also is a real number, right? So I'm not dealing with any complicated vectors, though you can actually extend this for multivariate Gaussians as well. Just becomes a little bit more tricky, okay? So you take the derivative with respect to mu, set it to 0, right? The first term is independent of mu, right? So this becomes 0. There's no derivative with respect to mu over here. It just depends on sigma, okay? So all you're left with is this term. You take the derivative with respect to mu, right? You get exactly this term. You get the sum of xi minus mu divided by sigma square should be equal to 0. You just rewrite this a little bit. You will get exactly this. You will get n times mu, right, minus sum of I from 1 to capital N of xi divided by sigma square, right? You sigma square, you just multiply sigma square on both sides. Since this is equal to 0, sigma square goes away, right? What you essentially get is that the mu MLE is nothing but the empirical mean, which is 1 over n, the sum over I from 1 to n of xi. Okay, so this makes a lot of sense, right? I have my data points x1 to xn. I take the empirical mean of my data points, right? And I compute this empirical mean. This is exactly the MLE estimate, okay, for a Gaussian distribution. Does it make sense? Any questions so far? So this is pretty straightforward, right? All I'm doing is computing the maximum likelihood and computing this for a Gaussian distribution, right? Or for a normal distribution. As you pointed out, a Gaussian and normal distribution were the same. Okay. So next what we do is that we can repeat the same thing for the variance, right? So my second parameter is sigma. So I need to compute the derivative with respect to sigma, right? So it's a little bit of math over here, but it's kind of the same thing, right? So I compute the derivative with respect to sigma square. Now my first term actually has sigma square, okay? So the derivative won't be zero, right? But there is log of 2 pi sigma square, right? So I just expand the math around. You will see that the derivative of this is nothing but minus n over sigma. Okay, just a simple derivatives. Just need to work this out. You will see that this is minus n over sigma. Okay. The second term is the derivative with respect to sigma of minus the sum over I from 1 to n of xi minus mu the whole square divided by 2 sigma square. Okay. Again, this is, I don't need to care about mu. I'm just taking the derivative with respect to sigma square. Okay. Because there is 2 sigma square in the denominator, after taking the derivative, I get actually sigma cube over here. Again, I work this out a little bit. I get that the sigma square MLE is actually nothing but 1 over n of the sum of I from 1 to capital N of xi minus mu MLE the whole square. Okay. So this is actually interesting. So this also is kind of the sample variance, right? This is the so-called sample variance. When I compute my xi's, I have my x1 to xn, right? And I compute this. This is my sample variance. But it turns out that this variance is actually biased. Okay, so what does it mean by biased? Can someone tell me what does it mean by biased? What do we mean by biased over here? Okay, Nathan?
For how I see it, seems like we're computing a value based off of a previous computed value that might not really be the true value as well. But
Okay, so what do you mean by previous computed value?
well, we're calculating the variance for the maximum likelihood estimation based
Mm-hmm.
off of our value that we came up
Sure.
for the mean, where the mean's the maximum likeliness for that. It might that mean might not have been true as well, and so our variance is premised on the fact that the mean is right, which it might not be.
Yes, you're kind of heading in the right direction, but I think, but what we mean by biased over here is slightly even more easier. What this means is that once I compute this maximum likelihood sigma square, okay, so basically assume inherently, right? Inherently, we know that each of my xi's follow a normal distribution with mean mu and variance sigma square, right? So that means that there is some underlying mu and sigma square. Okay. So what it means by biased is that the expected value of my sigma square MLE, right? I compute my sigma square MLE from my data and I look at this expectation of this quantity over a lot of different data sets. It turns out that the expectation of this value is not the same as sigma square. So sigma square, this is my true sigma square, right? It turns out that it is not the same. But before coming to variance, let us just look at the mean first. Okay. So my again, I have my xi's distributed as normal from mu comma sigma square, right? Let us just look at the mu MLE parameter. Sorry, mu MLE, right? And my mu MLE. So I take my expectation of mu MLE. Okay. So mathematically, what is the expectation of this? This is nothing but 1 over n, right? And the expectation of this quantity, right? Which is sigma I from 1 to capital N of xi. right? So this quantity is actually nothing but um, 1 over n, right? I can take my I can basically take my expectations inside the sum. So I get sum of I from 1 to capital N, expectation of xi. Okay. So now each of my so can someone tell me what is expectation of xi? Mu, exactly, right? So each of my xi's are drawn from this distribution of mu comma sigma square, right? So the expected value of xi's will be mu, right? So it's a sum over mu n times is basically n multiplied by mu, right? So n gets cancelled. I have that this is nothing but mu itself, right? So what this means is that the expected value of the maximum likelihood estimator, okay, so this is an estimator, right? I'm estimating this from data. The expected value of this estimator is nothing but mu, right? So this means that this particular quantity is unbiased, okay? But the problem is that my variance is biased, and what this means is that if I compute the expectation of sigma square MLE, okay? Unfortunately, this is not equal to sigma square. Okay, and it's a little bit of involved math to actually compute this, but I'll just give the main ideas. Okay, so what we can, similar to how we did this for the mean, right? We can go ahead and compute this for actually the variance as well, right? So this is sigma square MLE. I'll just give you the main ideas here. So this is 1 over n. Again, I take the expectation inside, so there's nothing great over here, and I have essentially this is xi minus mu MLE square. Okay. So then what you do is that you basically can expand this term out. Okay. So this term is, so this you will get as nothing but 1 over n sum of I from 1 to capital N. Okay. And then you get essentially that this is expected value of xi square. Okay. Minus 2 multiplied by expected value of xi, okay, multiplied by mu MLE plus mu MLE square. So sorry. Okay, there is an expectation over here. Oh, sorry. So this is an expected value. Sorry, this is an expected value of mu MLE square. No. So this is, so it's not so it's actually the expectation of mu MLE square. Yeah. Okay. So and then this is like this is the sum of this entire quantity. So it's a little bit more involved. Okay. You can use the identity. So I'll just add one more page over here. Okay. So you can use the identity that the expectation of x square. Okay. The expectation of x square is actually the variance of x plus the expectation of x the whole square. Okay. So you need to use this identity over here because you have the expectation of xi square, right? And then you have the expectation of mu MLE square over here, sorry, right? So you just have to juggle around, right? What you will actually see is that finally you will see that sigma square MLE is actually equal to n minus 1 over n of sigma square. So as n goes to infinity, right, as n becomes very large, sigma square MLE becomes closer to sigma square. But when n is not large, when n is finite, there will be a difference between sigma square MLE and sigma square. Okay. So again, I'm just giving you the high level idea, the high level intuition here for computing this. Okay. So yeah, this is what I said, right? So the unbiased estimator is actually nothing but 1 over n minus 1 of this quantity. So if you do a 1 over n of this quantity, which is what the sigma square MLE is, right? This is not the unbiased estimator. So in fact, this quantity is actually equal to um, n minus 1 over n of the sigma square unbiased. And the sigma square unbiased is nothing but sigma square. Okay, so xi's again are a normal distribution of mu comma sigma square, right? Is this clear to everyone? Any questions on this? Okay. Okay, so I am not actually going over the MAP estimation for maximum likelihood, but actually I have a homework question on the MAP estimation for Gaussian distributions. Okay, so that will essentially with that you should be able to compute the MAP distribution of the Gaussian distribution, and I mean MAP estimation, right? And then I think we will try to contrast between the MAP and the maximum likelihood. Okay, so now what we'll do is that we will move a little bit to kind of classification problems. Okay, so we saw Gaussian distributions, and now we can talk about the simplest classification model called the Naïve base, right? But before that, let's just set this up a little bit. So I'm given features now, x, which is x1 up until xm, right? And the task is that I want to use this to predict a label y. Okay. Um, so assuming that we had a joint distribution over x and y, then given x, we could find the label using basically kind of inference, right? So I want to I want to basically find my label y, which maximizes the probability of y given x1 until xn. Okay, so this can also be computed using the Bayes rule. So basically, given if I'm given a distribution which is p of x1 until xm given y, right? Then I can compute this by using this probability multiplied by p of y divided by p of x1 until xm, right? Since this is independent of y, right? Since this is independent of y, I just basically maximize the product of these two, right? And then I take an argmax with respect to y. So let's look at a kind of example for this, right? So we'll be looking at um, classification of documents, right? So basically article or document classification. So imagine I have a collection of news articles, and each article has a topic associated with it with the article, right? So it's either a sports article, or it's an article on politics, or it's an article on science or technology, right? Or maybe finance, stock markets, etc., right? So I have a bunch of different news articles and I want to be able to classify these. Well, why is it important to classify this? It's important to classify this because I want to be able to segregate my articles, right? And secondly, based on the preference of users, I want to show certain articles, right? So if a user has preference for sports, I want to show more sports articles to the user, right? So basically document classification is a very important classification problem. And in some sense this is a very kind of nice kind of model for probabilistic modeling, right? Kind of nice example for probabilistic modeling. So let's look at this a little bit, right? So what is a possible feature vector? So over here, my instance, I have my xi comma yi, right? And this is my data set comprising of I from 1 to capital M. Okay, and xi here corresponds to a feature vector, right, slash article, right, and my yi corresponds to the topic of the article. Okay, so how do I come up with my so okay, so maybe again I'm using slightly bad notation here. So let's assume that x superscript y and y superscript y are um, my um, kind of feature vector, right? So this is my ith instance. So I have okay. So my x sub I now, right, corresponds to the ith feature in my entire feature vector x. Okay. So one way we can define this feature is that we can define xi as corresponding to the ith word. Okay, so xi can take a different value for each word in the dictionary. Okay, so imagine you have an article like this, right? So this is basically one particular article, and I think this is actually an article from 20 news groups data set. So 20 news groups actually is a classification data set. I think it's 20 news groups or something similar to that. Okay, so this is the particular topic, right? So it's sports dot hockey. So this is like a hockey article. Okay, so each of my words here, I want to store my words as my feature vectors. Okay, so one way to do this is that I can essentially, given a setup like this, I can define x1 x2 as a sequence of words in a document, right? So essentially x1 here corresponds to the first word in the document, right? X2 corresponds to the second word in the document, and so on and so forth, right? So here I'm essentially considering order as being important. So I go from x1 to x2, right? So it's basically this ordered feature vector. Imagine that my article has 1,000 words, right? And each xi basically is the ith word in the document, right? And now my word can be any word in a dictionary, right? So if my dictionary has 10,000 words, then you can see that this gets really large, right? So you have 10 raised to 4,000 possible words. This is not definitely not going to be possible, right? I mean, how can we really represent this feature vector? The main issue over here is that we were trying to represent the order between words in a document, right? So I was saying that I have xi as my first word, x2, I mean x1 as my first word, x2 as my second word, and so on and so forth, right? And doing this is really hard. Okay, so one assumption, and this is a very common model called the bag of words model. Okay, so the bag of words model says that I don't care what the position of the word in the document is. Okay, so as long as I have a word existing in a document, I want to compute the probability or the feature vector corresponding to that word, right? So, or in some sense, the assumption here is that I'm ignoring the order of the words, right? And all positions have the same distribution. Okay. Though it's a very simple model, right? I'm not really assuming any order over here, right? So I don't care if the word for comes before the word and, right? Or if it's a hockey document, I don't care if the word hockey comes in the first paragraph or in the last paragraph, right? The reason why this makes sense is because for most classification problems, it really matters on which word occurs and how many times the word occurs. Right? So the frequency of the words are important. It really does not matter as much as to where exactly the words occur in the document as much. I mean, you could use it a little bit, like, right? For example, like you can essentially add one more dimensionality in my feature vector where I segregate this into, like, say, you know, part one, part two, and part three, right? So if it's a very long document, then I can segregate this into three parts, right? So either the beginning, the middle, or the end of the document, right? And then I can add this additional dimensionality. This might improve the performance slightly, right? But I don't know to, but I don't need to go the full order. I mean, I don't need to consider the full ordering. I can consider this kind of partial ordering as well, potentially, right? But I think for now we'll just consider the simplest assumption where I don't have any ordering, And without any ordering, I'm just taking the bag of words model, right? So the bag of words model now is very simple. I have a document like this, right? I take each word, right, like the word total, okay, and that word total comes somewhere over here. I have the word, what word is there? I have the word gas, right? And the word gas comes somewhere in this document, right? So there's the word gas over here. I have the word oil. This document has oil somewhere. I have the word Africa here, and there is Africa here, right? So essentially, what I'm doing here is that each of my words I'm mapping into this feature vector, right? And this feature vector here stores the count of the number of times the word appears in the document. Okay. Any questions so far with this model? Okay, so even with the bag of words assumption, the problem is that if I were to look at the full-blown probability distribution, right? It's a probability distribution over P of x1, comma xm given y, right? The problem is that I need to compute this entire table, right? So if my feature vector is of size m, right? I need to compute this m dimensional feature vector. I mean this m dimensional probability distribution, right? So what that means is that for every possible value of x1 to xm, I need to have the count associated with it. Yeah. So professor, in the case where words like the yeah. So actually that's a good question. That is true that oftentimes there are these words that will come up which are not really important, right? So there are actually various tricks that are used in practice to minimize these words. Okay, so like one trick is, for example, you have a list of stop words, which are like the, in, and, which appear a lot, and those words are sometimes ignored in my model, right? And then there is also one more kind of slightly more advanced terminology called TF-IDF. I won't actually cover TF-IDF, it's slightly more advanced, right? But if you're interested, you can look this up. It's called term frequency and inverse document frequency. Okay, so this notion TF-IDF featureization exactly takes care of this issue. Essentially, to kind of talk about it at a high level, right? What TF-IDF does is that it looks at the words which appear throughout all my documents a lot, right? So words like the and in will appear everywhere a lot, right? Because they don't just appear in my current document, but they appear in all documents a lot, right? That's why you have this kind of term frequency and inverse document frequency, and because of this normalization, such words will actually be less valued. On the other hand, there'll be words which are very specific to this document, right, which appear a lot in this document. So for example, if it's a hockey document, the word hockey will appear in the document a lot, but it will not appear in all documents because hockey will appear in very few documents, right? So in my TF-IDF featureization, hockey will have a very high weight because it is very important to this document. So anyways, so there are too many probabilities, right? So if I want to compute, yeah, so the word will have a high value. Um, yeah, exactly. So that's the idea of TF-IDF. Okay. So, all right. So let's see. So, yeah. So the assumption made over here, in order to handle these probabilities, right? How do we handle these large amounts of probabilities, right? Probabilities, right? So the assumption made over here is that I can make some kind of a conditional independence assumption. Okay. So what this means is that given two features x1, x2, I'm assuming that the probability of x1, x2 given y is equal to probability of x1 given y multiplied by probability of x2 given y. Okay, and you can actually expand this to m quantities, saying that the probability of x1 until xm given y is nothing but probability of x1 given y multiplied by probability of x2 given y, right, until the probability of xm given y. So it's a multiplication of these m probability quantities. Okay, so this is what the conditional independence assumption is. and this is exactly the naive Bayes assumption. Okay. I think because we are out of time, I think we'll end over here. And I think we have a few more slides to go before this. We'll actually finish this up next time. So we'll start with the conditional independence. We start with the conditional independence next time. Okay. Any questions until now?